Okay, so this second part of radicals and rational exponents is going to start off with us rationalizing denominators. The denominators will have two terms when this is something that we have to do, okay? So the denominator contains a radical, so that of course is this guy here, expression, a radical added to another number, then you must do a little twist, and that is multiplying conjugates here. So what ends up happening here is you're going to change the sign in the middle. So if it's addition, you're going to multiply by a subtraction in the middle. So as you multiply these guys, what ends up happening, and you'll see it, I think, more clearly when I work one out like this, is you end up essentially with just A minus B. So whatever was underneath that radical, with the subtraction sign in the middle. Because you flip these signs here, it's kind of like a difference of squares, which we'll look at when we get to factoring. But anyway, so let's just practice one. So again, you'll know you need to do this when your denominator has a radical and another number with it, okay? Broken up, with addition or subtraction, okay? So we're still going to accomplish getting rid of that radical. Notice that the end result here has no radicals in it, okay? So the way that we do that is we multiply by the conjugate, okay? So you're still looking at your denominator like with rationalizing a denominator. You just have to kind of change it a little bit more than you did when it was just a plain radical. So this says 5 plus the square root of 3, so we're going to multiply by 5 minus the square root of 3 over 5 minus the square root of 3. So it's going to involve some distributing, a little bit more than just rationalizing a denominator. 7 times 5 is where I'm going to get 35. 7 times negative square root of 3 will be minus 7 square roots of 3 in that numerator. And that denominator is where we'll do kind of 2 rounds of distributing. We'll distribute the 5 and we'll distribute the square root of 3, okay? So 5 times 5 is 25. 5 times negative square root of 3 is negative 5 square roots of 3. Extend that a little bit. So we distribute the 5 completely. Now we're going to distribute the square root of 3. So square root of 3 times 5 will be 5 square roots of 3. And the square root of 3 times the negative square root of 3, you got to pay close attention to the signs, will be minus the square root of 9, because it was essentially a positive times a negative. They're both underneath the radical there, so you do have to do that 3 times 3, okay? So in this denominator, negative 5 square roots of 3 plus 5 square roots of 3 will actually add up to 0, so you won't see those guys anymore. Notice that the square root of 9 is 3. So in this denominator, we're essentially looking at 25 minus 3. So let's go ahead and keep that numerator. 25 minus 3, of course, we know is 22. And we are done. So notice the end result is no radicals in the denominator, just like with rationalizing the denominator, okay? This denominator is 4 plus the square root of 5. Our conjugate will be 4 minus the square root of 5. 4 minus the square root of 5. So you'll see some distributing like we had before. 8 times 4 is 32. 8 times the negative square root of 5 will be negative 8 square roots of 5. 4 times 4 is 16. 4 times negative square root of 5 will be minus 4 square roots of 5. Square root of 5 times 4 will be 4 square roots of 5. And then square root of 5 times negative square root of 5 will be negative square root of 25. Let me make sure we get that sign there, okay? And that denominator, similar before, negative 4 square roots of 5 plus 4 square roots of 5 is 0. And you see minus the square root of 25, well, that's minus 5. So the numerator is 32 minus 8 square roots of 5, while the denominator is 16 minus 5, which is 11. Okay? So that is what that will look like. And then the next section here was just some examples that you can practice on your own, that had we been meeting in person, I would have given you all a chance to practice on your own, but I will probably work through some of these when we do our online meeting. Of course, happy to answer any questions. I'll also post the key, okay? Moving on to higher roots. I kind of mentioned at the beginning we would do some cube roots, fourth roots, things like that. So what's going to happen with higher roots, it's very similar to square roots, okay? That process of simplifying the radical where we broke it down into the prime factorization will be helpful, because now you're just kind of looking for groups of 3 or groups of 4 to be able to get these guys out of the radical, okay? So it is helpful. I know probably not too common to have many of these cube roots or fourth roots kind of, you know, right on the top of your head, but it is still helpful to know that, like, cube root of 8 is 2, cube root of 27 is 3, and so that basically means that 3 cubed, 3 times 3 times 3 is 27. 4 cubed, 4 times 4 times 4 is 64, okay? Fourth roots, fifth roots, just a few that are probably helpful to kind of try to remember. If not, you know, you always have a calculator, okay? So same things we talked about before, that the product can be broken down or put together, and same for quotient. So similar rules here, okay? So cube root of 24, you're going to see me break it down very much like I did in the beginning a lot of the time, just because I think it's helpful to kind of see this broken down. So 24, you could think about it as 2 times 12, 3 times 8, 4 times 6. The list goes on, but when you go to create the prime factorization, it should always be the same, because you're going to go all the way down to prime numbers, okay? So here I am breaking this guy down. And the index is 3. I'm looking for the cube root of this guy. So I've got 2 times 2 times 2 times 3. And I just like to keep those like numbers together. I will be circling them in groups of 3 to see if I can get anybody out of that radical, okay? So there's a group of 3 2s. Know that 2 times 2 times 2 is 8, right? Well, the cube root of 8 is 2, okay? So we get to bring a single 2 out. We circled a group of 3 2s. We're bringing a single 2 out, having to leave the little 3 behind. So we do want to be sure index of 3 gets in there too, okay? So on the next one, the little indexes match. So it is acceptable to go ahead and say, okay, I'm looking for the fourth root of 32. Because, of course, 8 times 4 is 32. Now, what I would do, because it just helps, I think, to break this guy down. Maybe you look at him and you're like, oh, he's 8 times 4. The 8 breaks down into 2 times 4. And 2 times 2. So he's breaking down to a whole bunch of 2s. You can see I was able to circle 1, 2, 3, 4, 5 2s. So 1, 2, 3, 4, 5 2s. Okay. I will be circling them in groups of 4 to see if I can get anybody out of here. So I get to circle a group of 4 2s. So we'll be bringing a single 2 out and then leaving a single 2 behind, because this lonely guy didn't have anybody to join up with. Okay. 2 times 2 times 2 times 2, you probably know is 16. Okay, the fourth root of 16 is 2. Okay. We can break this guy down into the fourth root of 81 and the fourth root of 16. When we just talked about, that was 16. The fourth root of 16 was 2. So we'll go ahead and knock that out. 81, you probably know, is 9 times 9, 3 times 3, 3 times 3. So the prime factorization of 81 is 3 times 3 times 3 times 3. Well, if we circle these guys in groups of 4, that's perfect. A group of 4 3s bringing out a single lonely little 3. And nothing was left behind in those radicals. I didn't break him down, but had I know, I kind of did something similar here. It would have been just those 4 2s, and he got to come out, okay? Here again, these are like indexes with those 5s. It's completely acceptable to go ahead and go, okay, I'm trying to find the fifth root of 40. So I'm going to see if there's anything that will help here. I know that 5 times 8 is 45 is prime. 8 breaks down into 2 and 4, 4. So notice as you come back over here with the prime factorization of 2 times 2 times 2 times 5, there isn't anything that we can circle 5 of. So this guy doesn't simplify any further than that, okay? With these like indexes, you know, you are able to add and subtract as long as they match under the radical, which as it stands, they don't, okay? So we're going to break down the 16, keeping in mind we are doing the cube root of that, okay? So 16 we know is maybe 2 times 8. 8 is 2 times 4, and 4 is 2 times 2. So 16 is 2 times 2 times 2 times 2. Circle them in groups of 3. Okay, there was already a 5 out there. I get to bring a single 2 out. 5 times the 2 that's coming out is 10. times the cube root of the long little 2 left. That was this guy simplified, okay? So we're going to minus 11 cube root of 2. So now we're getting somewhere where we can actually subtract these guys, okay? So 10 cube root of 2 minus 11 cube root of 2, you could think about it as negative 1 cube root of 2. And a lot of times we don't really put the 1 there in these sorts of cases, okay? So it's certainly possible to see it as something like that, okay? The next little section is several practice problems, just kind of looking at some different higher root sort of problems. Next thing I'm going to work through with y'all is these rational exponents, how we can rewrite radicals as rational exponents, okay? So rational exponents provide a way of representing the same value as a radical, but without using a square root sign. So it writes a radical as an exponent. That's where we're getting this word rational exponents, okay? So what we want to understand about the exponent that is created. Your generic square roots, your usual plain square roots like this guy here, has an understood index of 2, okay? And so when you go to create his exponent, this guy becomes your denominator of your exponent, while the power that is here becomes your numerator. So that's why you see him written as 36 to the 1/2 power, because the index of 2 ended up in that denominator, while the first power essentially ended up in the numerator. So here's the index of 3 ending up in the denominator, and the power of 1 ending up in the numerator. Okay, so the index determines our denominator, while the power determines our numerator. And that's basically what is being explained in this little area here, okay? And then they go back to our negative exponents that we discussed in a previous lesson, okay? So what we're going to do on these is we're going to actually solve these guys, okay? So know that the denominator is your index, and then the numerator, if you want to write it, is kind of your power. So we're basically essentially looking for the square root of 64, which is 8. Now we're essentially looking for the square root of 25, which is 5. This negative sign in front here just goes out in front of whatever radical we're coming up with. Well, he'll be our index. So the 4th root is 16. We saw it a couple times a second ago. I'll just go ahead and tell you it is 2. Throw your negative sign in front of it. We're looking at negative 2, okay? This is got parentheses around it, so that operates differently than the negative sign just hanging out in front, okay? So we're looking to find the cube root, because that's the denominator, of negative 27, okay? So those odd indexes do operate much differently than those even indexes, because it's certainly possible to get a negative number when you have an odd index. So know that 27 is 3 times 3 times 3, and therefore negative 27 is negative 3 times negative 3 times negative 3, because that would be your positive 9. Then it would be a negative 27. So we can come up with an answer of negative 3 for the cube root of negative 27. Here again, you've got it in parentheses. So that entire 64, we're going to recognize that he is being carried to the negative 1/3 power. So it's essentially 1 over 64 to the 1/3.